Following the Beirut explosion, Google experienced a spike in the number of searches containing the term ammonium nitrate. Though we are not qualified to explain the political and socio-economic causes that led up to the explosion, we believe that we can offer some scientific and historical insight towards ammonium nitrate explosions. Keep in mind, though, that some of the science that we are presenting here is simplified, and that there is more to be said about this topic. To begin, this was not the first time that such a disaster was caused by large stocks of ammonium nitrate. In 1921, a devastating explosion caused by a large stockpile of ammonium nitrate and ammonium sulfate stored in a BASF production plant in the German city of Oppau resulted in a final death toll of 560 people. This plant, at the time, was one of the first to mass-produce ammonium nitrate, a key ingredient in the manufacturing of explosives for the war effort, using the Haber process. The heterogeneous mixture of ammonium nitrate and ammonium sulfate in a 20-meter-tall silo, collapsing under the weight of the ammonium nitrate that absorbed moisture from the air, was turning into a hard lump that, if left alone, would become useless. In the face of potentially losing profits, the workers inserted dynamite charges into the mixture to try and loosen it up before digging it out. The detonation of these dynamite sticks resulted in an explosion that formed a crater that was approximately 19 meters deep and 108 meters in diameter. After this event, large factory explosions caused by ammonium nitrate became less and less frequent as the safety guidelines for large-scale ammonium nitrate storage and production procedures were refined. However, with the growing global economy, explosions caused by unattended ammonium nitrate stockpiles in ship ports became more and more common as large shipments of ammonium nitrate were often left for months at ports waiting for its next ride. In 1947, a disaster similar to that in Beirut unfolded in the port of Texas City, caused by the rapid decomposition of a large sample of ammonium nitrate on a French-registered vessel. The explosion leveled more than 1,000 buildings surrounding the port, creating a shockwave that shattered all windows within a 16-kilometer radius of the blast site and blasted 2 sightseeing planes out of the sky. More than 5,000 people were injured from the explosion, and a total of 567 deaths were accounted for. To this day, this event is commonly regarded as the worst industrial accident in American history. For the next few decades, the guidelines for long-term ammonium nitrate shipments were adjusted once again to reduce the risk of explosions. But in 2015, an incident similar to the one before occurred in the port of Tianjin, consisting of 2 separate explosions, both caused by large samples of ammonium nitrate stored in storage containers. The 2 explosions in total amounted to an energy equivalent to that of around 100 gigajoules, approximately the energy released by an explosion of 28 tons of TNT, creating a shockwave that shattered windows in the 3-kilometer radius. Official reports released by the Tianjin city government amounted the total casualty count to 173 deaths and 797 injuries. And in this year, an unfortunate incident that shares striking similarities with the former 2 occurred at the port of Beirut, Lebanon. As most of us have probably heard already, the devastating explosion was caused by the detonation of around 2,750 tons of ammonium nitrate stored in a warehouse for 6 years. The explosion, the most devastating industrial accident caused by ammonium nitrate since the one in Texas, created a crater approximately 43 meters in depth and 124 meters in diameter. Hundreds are dead as a result of the immediate explosion, and thousands more are injured, hungry, tired, and homeless. To this day, the total number of deaths caused by the explosion has not been summed up by any official institution, and the residents have yet to recover from the explosion. Food shortages, which were already a common sight in light of the COVID-19 pandemic, worsened as large amounts of grain and storages were destroyed in the explosion, and with the lack of running water and access to immediate health care, many are hungry, injured, and tired on the streets at this very moment. What do these former 3 explosions have in common? They were all ultimately caused by a rapid decomposition reaction of ammonium nitrate, but more importantly, they were all triggered by a fire of some sort. Once the fire started, the municipal firefighters struggled to put it out, for ammonium nitrate, like potassium nitrate and other salts associated with explosions, is a strong oxidizer when heated. At the most basic level, an oxidizer is a substance that can accept the electrons of other species, a process that releases large amounts of energy in a combustion reaction. Combustion reactions, such as the burning of sugars, takes place in the presence of oxygen gas, so normally, in the absence of an oxidizer, the fire can be put out by simply starving the system of oxygen gas. But when an oxidizer is present in the reaction, it is a lot more difficult to slow it down, as there is a constant, fresh supply of oxygen atoms for the reaction to continue. In the case of Beirut, Tianjin, and the Texas explosions, the fires that ultimately caused the ammonium nitrate to rapidly decompose could not be put out due to the presence of ammonium nitrate acting as an oxidizer. How does ammonium nitrate explode, then? Normally, under room temperature and standard pressure, ammonium nitrate doesn't decompose at a quick rate. Yes, ammonium nitrate is still decomposing under normal circumstances, but it does so at a rate that is so slow that, at a macroscopic perspective, we consider the decomposition reaction to not be occurring at all. The story changes, however, when a sample of ammonium nitrate is heated to 260 or 270 degrees Celsius. As the temperature of the sample approaches this margin, more and more particles have enough average kinetic energy to meet the activation energy for the decomposition of ammonium nitrate. Or, in simpler terms, the particles start jiggling fast enough so that when they smash together, the kaboom occurs. Under standard conditions, we calculate that the decomposition reaction of ammonium nitrate has a change in Gibbs free energy of negative 224 kilojoules per mole. What does this number mean? In short, the decomposition reaction is pretty complete, and it releases quite a bit of energy, mostly in the form of heat. This heat then is transferred to other ammonium nitrate species, which then undergo the decomposition reaction themselves to release more energy. Keep in mind, though, that this calculation only serves as a rough estimate, since the actual decomposition of ammonium nitrate releases a variety of different nitrous oxides. From these results, we expect ammonium nitrate to readily detonate once it reaches this temperature, though this is not the case in real life. If you tried heating up a sample of ammonium nitrate, not that I'm saying that you should though, in an open container, you would most likely notice that the sample dissipates away into toxic colorless nitrous oxides with water vapor. A source of heat by itself is not enough to cause ammonium nitrate to detonate explosively, as demonstrated in this video. What then causes ammonium nitrate to rapidly decompose? The key lies in a quick, sudden burst of energy, usually in the form of an external explosion or the confinement of the rapidly expanding gases that result from the reaction. In all three aforementioned cases of ammonium nitrate explosions at the ports, the ammonium nitrate samples were contained in shipment containers of some sort, and during the fire, small explosions from the combustion of other nearby compounds and fuels triggered the eventual decomposition of the entire ammonium nitrate sample. These miniature explosions caused a part of the bulk sample of the ammonium nitrate to undergo rapid decomposition, releasing a pressure shock wave very near the unreacted parts of the sample, pushing more nearby ammonium nitrate to detonate. Once one part of the bulk ammonium nitrate sample underwent rapid decomposition, the rest quickly followed suit due to this feedback loop. And once this feedback loop is established, we get a quick expansion of gas consisting of superheated water vapor and nitrous oxides, resulting in the catastrophic kaboom that we see.
Oh my god! الله عمل ذرة هيدي يا صورت أطرى دخيل شو رايكم؟ يا أطرى دخيل شو رايكم؟ يا عم طفى ما في حدا منهم يا أطرى دخيل لحن ربك شفت الهزم ما في حدا منهم روح عم دق لميشا يا فراس خليني دق لمرتي تكي